Good morning, everyone. Last time we started talking about the general angular momentum commutator algebra. So angular momentum commutator algebra. And so this involves a general angular momentum operator, which we're going to write as J. J is equal to, it's a vector of Hermitian operators. Okay, and then we also found it convenient to define its magnitude squared, which is just the sum of its rectangular components. So that's also a Hermitian operator. Okay, and we're being very general, so I'm not telling you how to construct these things out of other operators, except that there is a special case where we can do that. Okay, if J is equal to what we called L, which is defined to be R cross P, then that's a special case that obeys everything that I'm about to tell you today. But I don't want to commit to that specifically. I want to say, if something obeys the angular momentum commutator algebra, then it will obey lots of other properties. So the commutator algebra in terms of these operators is defined by saying the commutator Jx with Jy is equal to IH bar Jz. And then permutations of that, Jy with Jz is IH bar Jx. And Jz with Jx is IH bar Jy. So anything that satisfies those, we define to be an angular momentum, regardless of where it came from. And then from that, we derived that if you take the commutator of J squared with any of the components, that's 0. So all of these things are 0. Okay, and so our job is to figure out as much as we can about the eigenstates and eigenvalues of these operators as we can. Okay, so let's start with a useful fact. We're actually going to derive a whole bunch of useful facts today. This is just the first of many. Is that the eigenvalues of J squared are going to be non-negative. Okay, now, whenever in quantum mechanics you're asked to prove that some eigenvalue of something is non-negative, of some observable is non-negative, the strategy is almost always exactly the same. And in fact, the proof that I'm about to show you that the eigenvalues of J squared are non-negative is something very similar to what we did for the Hamiltonian of the harmonic oscillator. Okay, so proof. Consider any ket psi, and consider the following thing, the expectation value of J squared. So then psi J squared, psi is equal to, we're just going to put in the definition, and I'm going to split up the Jx's as I'm doing here. Oops, not equals, plus. I'm just writing each one twice, each operator twice, using the definition of J squared. And the reason for doing that is because now I can write this as a sum of norms. So this is the norm of Jx acting on psi squared plus the norm of jy acting on psi squared, plus similarly for jz. And the reason for doing that is because remember the definition of a norm is that it's always a non-negative real number. So this is greater than or equal to 0. This is greater than or equal to 0. And this is greater than or equal to 0. And so the whole thing is greater than or equal to 0. Now there was one tricky thing that I did here when I said that, for example, this was equal to the norm of jx psi squared. That relied on the fact that the jx is Hermitian, because otherwise this should have been a jx dagger, but jx dagger and jx are the same because they're Hermitian. So here I have used the fact that jx and jy and jz are Hermitian. It makes sense that I would have had to use a fact like that, because otherwise this proof would work for almost any operator. And it's not true that any operator has non-negative eigenvalues. So actually that was just for the expectation value. Now we have to make it a statement about the eigenvalues, but that's not too hard, because in particular, let's say our state was an eigenstate of j squared, and see what happens. So in particular, if j squared acting on psi was equal to some eigenvalue acting on psi, then when we take the expectation value, we can just pull out the factor of lambda. Okay, and the norm of psi is always non-negative. And so this is greater than or equal to 0. Okay, and so that tells us that lambda must be also. Because the only way to get something positive, if it's the product of something times another positive number, is if it itself is positive. By the way, the only way that it can be equal to 0 is if, in fact, psi was the null ket, or lambda was itself 0. All right. So lambda is greater than or equal to 0. That's the eigenvalue of j squared. And now it's convenient to make a definition. Let's define that lambda to equal h bar squared times j plus 1. Okay, so this is really defining what j is. We're defining j for an eigenstate of j squared in such a way, this should be h bar squared, sorry, in such a way that the eigenvalue is h bar squared times j plus 1, which I'm kind of pulling out of my hat at this point, but that's because I know where we're going, and I know that it's going to work out nicely. So if we do make that definition, then we learn the following things. We can just solve for j. So j is equal to, you solve the quadratic equation, and this is square root of lambda over h bar squared plus 1/4 under the square root minus 1/2. Okay, and so now if you stare at that and you say, oh, lambda is positive, that means this number is a number greater than 1/2, and then we're subtracting 1/2. So if lambda is positive, as we proved, then j is also, I shouldn't say positive, I should say non-negative. Then j is also non-negative. Okay, so that's because lambda, we proved, is non-negative. Okay. All right, now, because j squared and j sub z are Hermitian, and they commute, we can choose, if we want to, So they commute their Hermitian. We can choose, if we want to find an orthobasis of their common eigenstates. We had a theorem to that effect. Can find an orthobasis of common eigenstates. And so let's write down what those look like. So that if it's an eigenstate of j squared, I'm going to label it by a label k, and then another label j, and then another label m. And I know its eigenvalue is h bar squared j times j plus 1. And then I get back the original state. Okay, and similarly for j sub z. Except that now it's h bar times m times k times j times m. Okay, so what are these labels? J is the label for the j squared, m is the label for the eigenvalue for j sub z, and k, whatever it is, and we're not going to be specific about it for a while, is some degeneracy label. It just reflects the fact that there's no guarantee that if I tell you what j and m are, that will uniquely determine the state. There might be lots of states that have the same j and m. It depends on the problem. So these are degeneracy label or labels. Depending on the problem, I might actually need more than one label to distinguish the different states that have different j, that have a specific j and m. But just for example, this would be for the harmonic oscillator in 3 dimensions. This is what we called n. It's the energy level. So for the 3D isotropic harmonic oscillator, we had this other label that turned out to be the energy. So for the point of view of angular momentum, that's a degeneracy label. N is a degeneracy label. From the point of view of the energy, then J and M are the degeneracy labels. They're the things that distinguish different states that have the same energy as opposed to different angular momentum states, or sorry, for different energy states that have the same angular momentum. Okay, so in general, that's what the eigenvalue problem looks like that we're going to try to solve. And the theorem told us that we had an orthobasis of this. So we're going to insist that that's true. And so it's true that if I take the inner product of two of them, labeled by k, j, and m, and k prime, j prime, and m prime, that's going to be 1 if and only if k and k prime are the same, and j and j prime are the same, and m prime are the same. Okay, now, if you just take some state that's an eigenstate of j squared and j sub z, it may or may not be orthonormal. But what the theorem tells us is that you can always choose them to be orthonormal. And then if you're unlucky and it wasn't, the basis you chose wasn't orthonormal, then you might have to do Gram-Schmidt process on them to make them be orthonormal. Okay. Now, about this M thing, this M label, for the special case of orbital angular momentum, so that's when J sub z equals L sub z equals xpy minus ypx, then we found that M was an integer. But today we don't want to assume that because again, we don't want to commit if we don't have to. Okay, so now this is the eigenvalue problem that we're trying to solve. We're trying to find simultaneous eigenstates of j squared and j sub z. And so we can ask the question more generally than angular momentum. Oops. more generally than orbital angular momentum, what J and M's are allowed? And if you've taken a class on quantum mechanics before, you're probably familiar with the answer, but we're going to go through and try to carefully prove it. So before doing that, it's useful to make some more definitions that will be useful tools in what we're going to do. And so we're going to define something that we're going to call J plus. J plus is defined to be Jx plus Ijy. And then we're going to define J minus to be Jx minus Ijy. So we've made a special choice by singling out Jz, and then whatever the other two components are, we define these combinations. And these are called raising and lowering operators for angular momentum, specifically for the M eigenvalue. And so they are similar in many ways to A, dagger, and A for the harmonic oscillator in one dimension. In particular, one similarity is that they're not Hermitian. So they're not eligible to be observables, but that's okay because nobody said that every useful operator had to be an observable operator. Anyway, they're sort of morally observable, even if they aren't strictly speaking observable, because they're built out of observables, right? Jx and Jy are observables. So even though these are not technically observables, they're built out of observables anyway. Okay, so now let's note a few things about these operators that are going to be useful. One is, if I take J plus and I take its Hermitian conjugate, that's equal to J minus, and vice versa. So that's useful because we might have an expression and we want to take the Hermitian conjugate of the expression, and we've written everything in terms of J pluses and J minuses. That tells us what to do. Another thing is, if I take the commutator of J squared with J plus, well, that's equal to 0 because J squared just commutes with Jx and Jy. So same thing for J squared with J minus. Okay, and we already know that J squared commutes with J sub z. So those are all 0. You can also compute that if you take the commutator of J sub z with J plus, that's just equal to H bar J plus. That comes from the commutators of Jz with Jx and Jy. Similarly, if I take the commutator of Jz with J minus, I get minus H bar J minus. And if I take the commutator of J plus and J minus, there's a sneaky factor of 2 times H bar Jz. Okay, so all of these things put together are another way of stating what the angular momentum commutator algebra is. Just rewritten in terms of J plus and J minus rather than Jx and Jy. So this is still the commutator algebra. Okay, some other things that are going to be useful are what happens if instead of taking the commutator, what if I just multiply J plus times J minus? And if I just go back to their definitions, I can rewrite that as Jx squared plus Jy squared. And then there's a cross term, which turns into a commutator, which then turns into a J sub z. So that's true. And then I can do it in the opposite order and get almost the same expression, except this turns out to be a minus H bar. Okay, and then if I want, I can take those two statements and put them together. It's useful to note that if I that this is a plus and that's a minus. So if I take their sum, that's going to cancel out. Okay, and so from that we learned that j squared can be written as the average of j plus j minus and j minus j plus if I just add in the jz squared part. Okay, and then from that, in turn, we learn that j plus j minus can be written as j squared minus jz squared plus h bar jz, and j minus j plus is j squared minus jz squared minus h bar jz. So the reason these things are useful is we're going to be writing down expressions that involve matrix elements of different combinations of jz and j plus and j minus. And so these give us ways of simplifying those matrix elements at the operator level before we have to figure out what they do on specific states. All right, so those are the tools we're going to use. And now let's write down a sequence of facts. So fact one, we've actually already seen. Fact one is just that j was a non-negative number if it's corresponding to the eigenvalue of the total angular momentum squared. Okay, and so fact two is the following, that m has to be between j and minus j. So more specifically, minus j has to be less than or equal to m, has to be less than or equal to j. Okay, so let's see the proof. So for the proof, we're going to consider, again, this is a theme that we've seen before. We're going to consider the norm of the state j plus jm. And the norm of any state squared has to be greater than or equal to 0. It's only 0 if it's the null ket. But now we can write this as jm, j minus, that's really j plus dagger, but I'm rewriting it as j minus, j plus jm. By the way, I should say that what we've done here is we're suppressing any degeneracy label there might be, which we called k before. And the only reason for doing that is because if we kept the degeneracy label, then throughout what I'm about to do, it would just do nothing. It would just be there and play no other role. And so it's just kind of distracting and a waste of time to write down the degeneracy label for what I'm about to do. For other things, you have to be a little bit more worried and keep track of degeneracy labels. And we'll get to that later. Okay, so anyway, this combination we have figured out has to be greater than or equal to 0, but now we can compute it. Oops. We can compute it using some of the tools we wrote above. So I'm going to choose to rewrite it as j squared minus jz squared minus h bar jz times j times m. So now we can see why this was a useful thing to write down. So we're actually stealing this expression right here. But the reason this is useful is because now everything that appears in the operator acting on this state to the right of it is a simple thing, because these are eigenstates of j squared and j sub z. So I can just write them down as numbers. This is equal to h bar squared j times j plus 1, that's for j squared, minus h bar squared m squared from the second term, and then minus h bar times h bar m for the third term. all of that stuff multiplied by Jm, Jm, but we assumed this was an orthonormal basis, so that's just 1. Okay, and this expression in parentheses we can simplify as h bar squared times j plus 1 minus m times m plus 1. Okay, and so there's a common factor of h bar squared that we can pull out, but what we've learned is that j times j plus 1 minus m times m plus 1 has to be greater than or equal to 0. And now we can rewrite that by factoring it. So we're going to factor the left-hand side, which we can write as j minus m times j plus m plus 1. That has to be greater than or equal to 0. Okay, and so now, since j is greater than or equal to 0, it must be true that m is less than or equal to j. So to see that that's true, suppose m was greater than j. If m was greater than j and j was greater than 0, then this part would be positive. But then if m is less than j, that tells us this part's negative. So we would have a negative number times a positive number supposedly greater than or equal to 0, and that would be a contradiction. Okay, so we have learned that m has to be less than or equal to j. And now, and this is another theme, anything that we can do with j plus, we can do with j minus just by flipping a few minus signs that you have to work out where they go. Right? So similarly, if we consider the norm of j minus acting on the state Jm and require that that's greater than or equal to 0, which it must be. So that implies j plus m, j minus m plus 1 is greater than or equal to 0. I'm skipping the steps there because they're literally the same except for changing some pluses to minus. Okay, and then that implies, again, since j is greater than or equal to 0, that implies that m has to be greater than or equal to minus j. Okay, and so that means when I put it together with this, that gives us the claim that we were stating in fact 2, that minus j is less than or equal to m is less than or equal to j. Okay, so m has to be between j and minus j inclusive. All right, so we will come back and use fact 2 in a little bit, but let's move on to fact 3. I didn't label them like this in the notes. Or label it because in the notes we have equation numbers to distinguish the different facts. But here in class, I don't have equation numbers, so I'm just calling them fact 1, fact 2, fact 3, etc. So here's fact 3, is suppose that I have an eigenket, and an eigenket is defined to not be null. So I'm going to write that as does not equal 0. Then, if I compute j minus acting on that thing, that will be null if and only if m was minus j. Okay, so sometimes if I have a ket that's non-null, I can act with j minus and make it null, but that only works if m is minus j. Okay, so let's do the proof. Now this is if and only if So the proof is going to have two parts. There's the if and the only if. So let's say m is minus j. Okay, then if I take what I have, j plus, and act on j minus, jm, okay, then when I go back to what j plus j minus was and I plug it in, I find out that's 0. So that's all there is to that, because that means that jm, j plus j minus, jm is 0, which would imply that the norm of j minus, jm is 0. And the only way the norm of a ket can be 0 is if it's the null ket. Remember, that was one of our basic postulates of a Hilbert space. And so that implies that j minus acting on jm was actually the null ket. Okay, so that's half of that's the if part of the proof, and now we need the only if part of the proof. Okay, and so for that, so also consider what happens if we take j plus acting on j minus jm. Okay, and once again, we're going to use, let me show you, let's go back up here and show what we're going to use. We're going to be using this fact, right? So the idea is to write things as much as possible in terms of j squared and jz's, because we know how they act on the eigenstates. They act and just give you back numbers. Okay, so going back to here, we're rewriting this as j squared minus jz squared plus h bar jz. Okay, which is h bar squared times, again, j times j plus 1 minus m times m minus 1. Okay, jm. Okay, and so if j minus jm is 0, we need, when we factor this, we need j plus m times j minus m plus 1 to equal 0. And so there's two ways that could happen. Either m is equal to j plus 1, or m is equal to minus j. So this right here was factoring into that. Okay, but the first one is impossible because that contradicts fact number 2. And so the only possibility left is that m is minus j. Okay, so it works either way. It's if or only if. That was fact 3. Fact 4 is going to be almost the same. Fact 4 says, if, again, we have a non-null eigenket, then j plus acting on it is null if and only if m is equal to plus j. So we're just flipping the roles of plus and minus here. And so I won't go through the proof because it's similar to fact 3. But with strategic pluses and minuses interchanged. All right, so now on to what we're going to call fact 5. So fact 5 says, okay, what if m is not equal to minus j? We already proved that m had to be between minus j and j. And so if it's not minus j, that means it's greater than minus j. And consider the state j minus acting on that state, jm. Okay, the claim is this has j squared eigenvalue that's the same, namely h bar squared, j times j plus 1. And it has jz eigenvalue that's h bar times m minus 1. Okay, so let's do the proof of that. The proof is, first of all, for j squared, if we act j squared on j minus jm, now we can use the commutator algebra to rewrite this as j minus j squared acting on jm plus the commutator of j squared and j minus. Okay, the commutator, though, was 0. And this, we know what that is because jm is an eigenstate of j squared. So this is just j minus h bar squared j times j plus 1. Okay, and so that's indeed telling you that j minus acting on jm is an eigenstate of j squared, and we pulled out the eigenvalue. There it is, which gives us that. Okay, that was the easier part. And then the harder part is the j sub z eigenvalue of this thing. J sub z acting on j minus jm is equal to j minus j sub z acting on jm plus the commutator of the two. Okay, and the first one is h bar m j minus. And then here we're going to use the commutator algebra. The thing we worked out said that that was minus h bar times j minus. And so the whole thing is h bar times m minus 1 times j minus. Okay, and that's proving that j minus acting on jm here is an eigenstate of j sub z with eigenvalue h bar m minus 1. So that was what we claimed there. Okay, so what does that say? That in words, what that's saying is that if we act with j minus, that's a lowering operator for m because it doesn't do anything to the j value, but it lowers the m value by 1. Okay, so j minus equals lowering operator for m. All right, fact 6 is going to be just a corresponding statement with pluses and minuses reversed. So fact 6 says if m is less than j, we already know that if m equals j, then j plus acting on it is 0. But if m is less than j, then j plus acting on jm has j squared eigenvalue unchanged. It's the same thing. And the j sub z eigenvalue is, well, first of all, it's an eigenstate of j sub z. And secondly, the eigenvalue is with m increased by 1. And so what we learned from this fact is that j plus is a raising operator for m. So j plus and j minus just decrease or increase the m eigenvalue. All right, now we're up to fact 7. Fact 7 is we're finally ready to prove that j is not just any number that's positive or non-negative, but it's actually some integer divided by 2. Okay, so for some integer n, and we know that it has to be non-negative, so it's a non-negative integer n. All right, so let's prove that using the previous facts that we've already proved. So to prove this, let's say we just choose any state, any eigenstate Jm. So start with some non-null Jm. And it doesn't actually matter too much what we start with, as long as it's non-null. And we're going to act p times. P is some integer, number of times that we're going to act with j plus. Okay, so what does that give us? That gives us jp to the pth power acting on jm. And what we learned from fact 6 is that each time we act with j plus, it just raises m by 1 unit. And so I should put here proportional, not equal, because we should worry about normalization factors. But this should be proportional to j m plus p. All right. Now, this must give 0 for some finite p. By 0, I really mean the null ket. Okay, because otherwise, if I chose p large enough, then I would have a ket j plus something, which would be non-null. And that contradicts fact number 2. Because fact number 2 said that the m value had to be between minus j and j, and here it's j plus something, right? Just by acting with p enough times. So the only way out is that m plus p has to equal j. For some p from fact 4. All right, so let's go back and look at what fact 4 was. So fact 4 said that if Jm is non-zero, then j plus Jm is null, if and only if m is equal to j. Okay, so that's saying that if we act with p enough times, we have to get m plus p equals to j so that this can be the null ket. Because if it's not null, that would contradict another fact, fact 2. Okay. Now we're going to do, as the theme calls for, anything we can do with j plus, we can do with j minus. And so similarly, if we act enough times with j minus, so if we have j minus to the q power acting on jm, that has to be proportional to jm minus q. And this must give the null ket 0 for some finite q. Okay, otherwise, we would have a non-null ket that contradicts fact 2 again, because otherwise we'd have j minus something. Okay, would be non-null. And that contradicts fact 2 again. Okay, and therefore, it must be true that for some q, m minus q is equal to minus j from fact 3. All right, so let's see where all this chain of logic has led us. That tells us that our m has to equal j minus p for some p, and it also has to equal minus j plus q for some q. And p and q are non-negative integers because they're the number of times we did this action of acting with an operator. Those have to be non-negative integers. Okay, and so for some non-negative p and q. And so if we take the second equality there and put it together, we get 2j has to equal p plus q, has to be greater than or equal to 0. So let's call that integer n. Since p and q are each non-negative, n is non-negative. Okay, and that's basically what we wanted to prove. We just divide by 2. So the allowed j equals 0, 1/2, 1, 3/2, 2, 5/2, etc. Okay, and we also had what the allowed values of m are, because the m's, one of them has to be minus j, one has to be plus j, and we can only step up and down by integers. And so the allowed m's are minus j plus 1, etc., up to j minus 1, and then j. And so there are 2j plus 1 of those. 2j plus 1 allowed values of m for a given j. So one thing I want to emphasize is that we didn't use anything about angular momentum other than the commutator algebra. We didn't assume that it was orbital or anything like that. And in fact, the orbital case is a special case of this, where the j's had to be integer and the m's have to be integer. Okay, but now there's an orthobasis of states that I'm going to rewrite. Again, there's some degeneracy label that I'm calling K today. Often we put the degeneracy label last, but for some reason with angular momentum, it's traditional to write the angular momentum labels last and the degeneracy for the other labels first. So these are other labels. This could be the energy. It doesn't necessarily have to be, but this depends on the problem. There I do have to commit to telling you what exactly the system is before I can tell you what these labels mean. Okay, and so the cases that we will do, we will treat in particular, we will go back to the 3D isotropic harmonic oscillator. Then we will do the hydrogen atom. Then we will do the free particle, which you might think would be easier, but in some ways is trickier than the hydrogen atom. Okay, but in any case, again, they obey orthonormality. In general, one decrees that it must be of this form. Okay, and so for the special case that we already found of J equals L, that's orbital angular momentum. We already found that the m's had to be integers. So that's consistent with the more general thing that it had to be some integer divided by 2. Okay, and so in that case, J equals L equals integers also. All right, so we're out of time for today, but next time we will consider what happens with subspaces of the angular momentum algebra, and in particular, what the form of the degeneracy labels can be. And we're going to find a remarkable fact that if you know one state that's an angular momentum eigenstate, then you can construct all the other states that have that same degeneracy label within it. Okay, and then we're going to learn, we're going to prove that it's possible, and then we're going to learn how to do it. All right, so that's it for today. So let me ask if there are any questions. Maybe specifically questions about the lecture first, and then we'll stop recording. Nothing specifically about the lecture for today? All right, let me stop recording then.